So hopefully everyone's making lots of good progress on your homework because it's due soon. Thursday. That's soon enough. Right, there'll be more. All right, so we've been talking about, and we'll continue to talk about the subject of classical versus non-classical. And in our case, we're talking about this in the context of optics. And, you know, one of the ways that we have discussed this is thinking about the source of life. And if we had a classical current, some current density function is based on it, we thought of as a classical field, then we would say that this gave us what we call classical light. And we have discussed many times now that that state of light can be thought of as some statistical mixture of coherent states, where we call this thing the Glauber-Sudarshan P-representation. And if this is a classical light, then this is some probability distribution, okay? And that's one way of defining something to be classical light. But as we were discussing at the end of last lecture, when we think about things from the point of view of quantum mechanics, what we know is what we measure. Know, of course, what does that mean anyway? But what I mean to say is all we can say is we do a measurement and we find something, and quantum mechanics tells us something about trying to predict what we're going to see when we measure. And the question of classical versus non-classical might be thought about not in terms of the source of the field, but what we measure about the field, and whether that can be described from a classical statistical theory or not. So the question is, you know, can we consistently assign probability we'll have an eraser. There's one. Yeah, everything moves around. It's, what I mean to say is a joint probability distribution to everything we could measure. Well, if we could do that, then that's classical statistical physics. And the degree to which we can't do that is the degree to which we say that our description of the system doesn't have this kind of classical description. And in that sense, we would say it's non-classical, okay? And so of course, we know that we can't do that, and part of that story is about what we might call incompatible observables or measurements. For example, famously, X and P. They don't commute. And because of that, in general, we can't assign a joint probability distribution to these observables, to measuring X and P. I mean, there's another sense in which we might say that classical physics differs from quantum physics differs from classical mechanics, is the notion of local hidden variables. Which is to say, when we assign a probability distribution to a measurement outcome, for example, an X or a P, if we wanted to say there was some kind of joint probability distribution, or for anything we measure, the question is, when we see that outcome, was that outcome there all along? Is it we just didn't know it? Like when we flip a coin, or whether this, cap is in my right hand or my left hand,
Neither hand.
Maybe. But no, it's here. But you discovered it, now you update your probability assignment, now you know it's going to be there the next time. But you discovered something that was there in principle, you just didn't have that information. And what is just inconceivable and something I can't even verbalize properly is the fact that there are outcomes that, there are effects that have no causes. And okay, maybe life is like that. Maybe life doesn't, there are effects that have no causes, but I want to know when that is true, because what are the things, what is the point of, how does measurement have anything to do with actualizing something? So these are still mysteries in my mind. And of course, this whole business is about entanglement. And this notion about incompatibility has different aspects of it, some of which are called contextuality and quasi-probabilities. And all of these are different aspects, distinguishing aspects of the quantum randomness that we see and our ability to assign probabilities to measurement outcomes that differ from the classical statistical. But, it's more than just a game of classifying quantumness versus classicalness. There's a question of the notion of resources for what we now call quantum advantage. So if there are these differences between the classical statistical theory and the quantum statistical theory, does it give us some kind of information processing capability beyond what is possible if systems obeyed this message? That's the whole story of quantum information science. And understanding which of these secret sauces are spicy enough or savory enough or whatever, sweet and spicy at the same time, to enable this is still an active area of research. Well, how do we, what is really important and what do we need to do actualize these things. And so the notion of classical versus non-classical might not have just a strict yes or no answer. There might be different degrees of classicalness versus non-classicalness, which allow different degrees of resources. So we're able to quantify better than in the past, at least my past, what we want, how we want to define something classical versus non-classical in terms of their resource for quantum advantage. Now we've seen some of if we think about the question of what we've thought about from the point of view of classical states as states produced by classical current, then we've seen some things that the non-classical states have as a resource different from the classical states. So the non-classical states in this context, which is P, not this, we could have sub-Poissonian statistics. That could be useful for reducing noise. We saw that we could have photon antibunching. Also potentially useful. And we saw that we could have squeezing. That's to say, we could have a quadrature which has a fluctuation that was below the vacuum level. And, these things were related to Glauber photon counting, right? Which were related to, normally ordered correlation functions like something like this might be some kind of nth order correlation function, the kind that we studied last semester, right? And the non-classical P representation is what required us to have super-Poissonian statistics or photon bunching. This squeezing is somehow a little bit different, right? And this was about measuring quadratures. It was a different kind of measurement. This was homodyne measurement, which was not a kind of direct detection of photon counting, right? And in fact, what we discussed last lecture was that we could understand the way squeezing happens in a perfectly good classical statistical theory on phase space in terms of parametric amplification and phase-sensitive stretching and squeezing, that a radio engineer would totally understand and say, that's obvious. I'm going to squeeze fluctuations or amplify fluctuations in a phase-sensitive way. And if I have noise, that noise is going to be reduced or amplified in a phase-sensitive way. And that was a perfectly good classical statistical theory of that. So in this sense, while it's true that there's no way that that could come from a classical current, it has a perfectly good classical description relative to this homodyne measurement, which is telling us there's something subtly different about these layers of non-classicalness, that the squeeze state is non-classical from this point of view, but classical from another point of view. And so we want to think about, beyond the Glauber theory of photon counting, we want to be able to think about other ways of expressing representations of, say, the state of the field that are related to different measurements we might do, not just normally ordered photon counting. And that leads us to the whole theory of phase space representations. So, we could define operators on a mode of the field that are the quadratures versus the number representation in terms of counting photons. This is related to the homodyne type measurement. This is photon counting. And to address this question, what we know is what we measure. We should think about what we measure and the representations relative to the measurements we're going to do. And that's what we're going to talk about this week and maybe into next. Now, I warn you, this gets kind of heavy math, okay? For those of you who aren't so fond of that, I'm sorry. We heard all about rounding optics last week. It's going to be a lot of mathy stuff this week, all right? So just brace yourself. All right, so I'll start easy on this and just remind ourselves of representation. So these are the quadratures of the field, but we can think about them just like the position and momentum of a massive particle. So I want to just review wave mechanics with some maybe new things, okay? Which is really representation in X or P, sometimes known as continuous variable quantum mechanics. As opposed to the discrete variable photon, right? So, well, that's simple. If I wanted to think about the position representation, when I'm thinking about, okay, there's a position operator. It has eigenvectors, which are the position eigenstates with position eigenvalues that are real numbers. And I can think about a representation. So this forms a complete set. The projectors are a POVM. They're a positive operator bounded measure, if I chose to call them as such. And as such, I can write any state or operator in this representation. In particular, I can think about the wave function, which is the position representation. Or I can just think about this from the point of view of the density operator. That's my probability distribution in X, probability density for a pure state, that is the square of the amplitude, psi star psi, which is the trace of rho with the POVM element or the projector, right? So that's my probability distribution. And that tells me the probability density if I were to do a measurement of the position, right? Now, the position representation is particularly simple if I have an operator that is only a function of the position operator. So if I had, for example, the potential, which is a function of the x operator, then I could say that the position representation of this is just the weighting of this, where v of x is v, where I just replace the operator by x, right? That would be the v of x is the representation, which is equivalent to this, right? Or equivalently, the trace of v with the projection operator. And of course, in this particular case, everything is all copacetic. If I wanted to look at, say, the expected value of that, that's just like in classical physics, I would have some probability distribution of x that would tell me what the average potential energy is, which of course is the same thing and more generally like that. It's the expectation value of that operator. Okay. Now here's something potentially new. Let me define the delta function, where this is an operator which has the following meaning. Like any operator that's a function of this, I can look at this, let me call this x0 just to be, so I don't have so many dummy variables, is this. So this is the operator, which is a weighted sum of the projectors, where just like I replaced x hat with x. Is that clear that this operator equals this? I could, if you like, put a complete set on each side. But this I can do, and this, of course, is this. So that's another way of writing the projector onto x. I should mention, if x had units of length, the kets actually have units, okay? They have to, because if they're the complete set, they have to have the units of 1 over the square root of length. So the delta function, you know, has units of 1 over its, whatever its argument is, right? So it's all self-consistent here. So the delta function, so I can also think about these representations as taking the trace with a delta function that replaces the operator x hat with the value x. That would give me the representation of this operator, particularly if it's a function only of x. It's a function of x and p, well, I have to do that. But it's still true, okay? So another way of saying this is, you know, if I were to look at the integral of this thing over all x, that's the identity, because this is equal to this. Okay. Now, that's, again, these are formal expressions. When we write a delta function, like, of course, this is x times the identity, you know, that's what it really means, but, you know, we're physicists, and so I can be sloppy forever. I said it on YouTube. Anyway, but we understand what it means. What it means is this, okay? Similarly, I could talk about the momentum representation. So firstly, I'm going to say h bar equal to 1 because I don't want to carry around my h bars. Okay?
So momentum is also inverse.
What's that?
So now momentum is also inverse.
Yeah, right. So I have the momentum operator, and I have momentum eigenstates. They're also real numbers. They also form a POBM, or complete set basis. And I can talk about the momentum space wave function. And I can talk about that also for a density operator. This is the probability that I'm going to measure a value p, which for a pure state is psi star psi in the momentum representation. And if I have an operator like the kinetic energy, then I can think about a momentum representation so this is some k of p, which is that, just like we had before, where k of p is k, where I set the operator equal to the eigenvalue. And that's the momentum space representation of the kinetic energy, which is this, which is this, which is this. So again, the projector onto momentum eigenvectors is equivalent to a delta function where the momentum operator is equal to p. Have you ever seen that before? Maybe, maybe not. But now you have. Okay? Now, in order to go between momentum and position representation, we remember the symmetries and the fact that momentum is the generator of displacements in position, and position is the generator of displacements in momentum, which is why they're related to the derivative, because those are the things that translate you through our remembrance of the Taylor expansion, good old calculus. So we have, this is the displacement in position. And this is the displacement in momentum. And from this it follows that if I look at the position representation of the momentum eigenvectors, they're plane waves. Okay? So this is equal to e to the I xp. Now, there's a choice of normalization that I will use, which is this one, consistent with these definitions of x and p, because if I look, for example, at either I. Of course, what this means is that the momentum space representation of the position eigenstates is the complex conjugate of this. Um, and that's just now gives us the Fourier relationship between the momentum space wave function and the position space wave function. So if I look at the position or the momentum space representation, we said that is equal to this, but now I can shove in a complete set. And in the wave mechanical way that I project this onto a momentum, I project this onto the complex conjugate of the momentum space representation, which is e to the minus I px over root 2. And similarly, we have the inverse Fourier transform. Both what we know is that both the position and momentum representations are complete. They're also orthogonal in the Dirac delta function sense. So if I look at the inner product between two position eigenstates, I can use the Fourier analysis to write it like that, right? I got the plane wave and the conjugate plane wave, which gives me this, which is equal to, and then we have to always get to remember our 2's and our pi's. There's going to be so many factors of 2 and so many factors of pi that will be all over the place and so confused in this business, but c'est la vie. This is a delta function. And similarly, we can do the same exercise, and that's true. So the plane waves, or the momentum space eigenfunctions, are a complete and orthonormal in this sense. And the position eigenstates, which are delta functions in position representation, are complete and orthonormal in the delta function sense. So I can express these functions in terms of either plane waves or delta functions and go back and forth between them through the Fourier transform. Okay. Now, one last piece in this wave mechanical story is another way of seeing this relationship, the projectors. Notice that we said that the projector on X was equal to this operator. And if I write that in this way, what I see is this is equal to right? That's this thing, but now I just replaced one of these guys with an operator. But notice this was equal to the displacement in momentum. So the thing that gives me the representation in X, or the delta functions in X, are Fourier transforms of the momentum displacement. Right? That gives me the delta function in X. Similarly, the projection on P which is the operator that is this delta function, I can write which is the inverse Fourier transform of the position displacement. Oh, I screwed up. I should use this board. Damn you, Deutsch. Anyway. I'll come back to this side of the board. So there are, again, I can express, if I like, because these things go back and forth, I can think about the position and momentum representation. Either the complete set of operators are the projectors onto the positional momentum, or the complete set of operators are the displacement operators, which are like, these are like plane wavy things, and these are like delta function things. But now, as operators, rather than functions. All right, with that said, we now want to think about phase space representations. Representations that are somehow in both x and p at the same time. Here we either had the position representation or the momentum representation, but what we're interested in is something that is a function of both quadratures, right? In the Pythagorean P representation, P alpha is a function of both x and p, the two quadratures, at the same time. And so we want to formulate a quantum mechanical representation in phase space. Now, it's clear we can't do that as an honest-to-God probability distribution. Otherwise, quantum mechanics is just classical Liouville statistical physics. But sometimes we can, and that will be our distinction between the classical and or a distinction as we build up this. So before I do that, I want to talk about, there's more formalism to come, and there will be lots of formalism. So let me think about a function on phase space. Okay, so I have a two-dimensional phase space for a single degree of freedom, or one mode. Some function of x and p. I can think about a Fourier dual plane. Now, usually we're thinking about p as the Fourier transform of x, or x as the Fourier transform of p. But now, I'm going to turn my head around, spin it like crazy. I'm going to think about a dual plane, which has a p1 conjugate to x, simultaneously, which is x1 that's dual to p. So this is going to be phase space, and this is dual phase space. In other words, there's the, time domain and the frequency domain, or the position and momentum domain, but this is kind of simultaneously at the same time. And the way we can do this with the 2D Fourier transform, which will have a particular convention. So I'm going to define the Fourier transform of this function in 2D. We've done 2D Fourier transforms before, but typically they're done like in two spatial dimensions, right? You have a beam, and you might say there's the x and y coordinates, and you're thinking about the Fourier transform in two spatial dimensions. But this is a phase space Fourier transform. All right? And so this, I'm going to have to integrate over both x and p, and I have a square root of 2 pi for both of them. So now it's a 2 pi. The function, and then I project it onto, and this is where the sign convention this is the convention I'm going to take. One of them has a positive sign, one of them has a negative sign because, you know, because of this duality with x and p, but this particular sign is the one that we will take for, it drove me crazy. I was trying to dig this out last week. I was like, why is it? Anyway, I need to go do my internal entry here. It's not, this is the way we do it, okay? So this is a 2D Fourier transform, okay? The dual to p is x1, and the dual to x is p1.
It's like, feel like a symplectic problem.
It's exactly that, yeah. Now, whether this outside sign is positive or negative is a convention, but this is the one we will take. I don't want to, we'll have maybe a homework about symplectic geometry. Yeah?
Does the sign even matter?
It doesn't have to be either, but we have to have it consistent so that all the notation will be the same, okay? And this is the one that we choose. If I take the inverse Fourier transform, I do it with the other sign. Right. And I can define, as I will, the 2D delta function. So this is a delta function in phase space. It would generally have the units of 1 over action if these things had units. But I'm not worried about that. They're dimensionless for us. Taking all the units out. And this will then have an integral over x over 2 pi, an integral over p over 2 pi, and then an e to the I have an x1 and a p1 minus I x1 x minus, oops, sorry, p1 times x prime plus I x1 p minus p prime. So that's a delta function in the two phase space coordinates, x and p. Often, as we know, we like to express our phase space amplitude in x and p as a complex variable. Let me just double check one thing. Sign convention here. Yeah, I got that backwards. Doesn't really matter, both are true, but I prefer this one. So, complex. Factors of 2, factors of pi, everywhere. So, we define the complex amplitude alpha as x plus ip over root 2, such that the real part of alpha is x over root 2, and the imaginary part of alpha is p over root 2. Then d squared alpha, which is d real alpha, d imaginary alpha, that's our integration element on the complex plane, is equal to dx over dp times dp over 2. Okay, so integrating, so let's look then, I can think about a function of x and p as some complexified version that's now a function of alpha and alpha star. It's the same thing, but one's a function, we think about them as a function of the real and imaginary parts, and the other we think about as a function of complex variables. Now, we really should think about this as a function of alpha and alpha star, because they are different, independent from the differential point of view, but often we just call this some function of alpha. We don't put alpha star in there, we just know it's there. So, with that, I can define, let me define beta as the dual variable, whose real part is x1 over root 2 and x, whose imaginary part is p1. Okay. Then I challenge you to show that minus I x1p minus p1x is actually equal to beta alpha star minus beta star alpha. Okay, because it's the imaginary part of this, right? That minus this complex quantity is twice the imaginary part of that. And similarly, is the conjugate thing.
Well, you need a factor of 2.
No, because of this root 2. Yeah. Yeah, like I said, they're everywhere. Okay, which means that I can write the Fourier transform. Okay, so if I look at the xtp over root pi, what this says is that the Fourier transform of this function is and the inverse Fourier transform is this. This is the same thing as this. Okay, just written in these new variables. So we think about the Fourier transform on the complex plane as a phase space Fourier transform, where beta is the dual of alpha, just like, okay? All right. So with all of that horribleness, there's more to come.
Yeah, can I ask a question?
Yes, please.
So, when you define the delta function, right?
Yeah.
In the previous book,
Yeah,
I don't understand the sign convention, because I thought the way you define the delta function is just you take in the inverse Fourier transform above, you take f star of x1 p1 as 1, right? Then, isn't there some issue with the sign convention there?
this is the complex conjugate of this.
Yes, I'm just saying if you take the f star of x1 p1 as 1, right? That should be 2 pi into delta function, right? The delta function that you've defined here, 2 pi into that should be just that equation value, right? F bar of x1 p1 as 1. So seems to be some issue with the sign convention.
Well, let's take a look at this. I could factorize this in terms of the product of two integrals. This is a delta function x minus x prime, and this is a delta function p minus p prime, which is what I'm calling this.
Right.
The fact that this guy has a positive sign and this guy's a negative sign is the convention we had by defining this in the first place. As we've discussed, I could have done this either way. I need to have this symplectic business. Whether I call this a minus sign or a positive sign was totally a choice of how I.
No, I understand that. I'm
Yeah.
just saying that, so that there's a minus sign when you do the Fourier transform, that is when you have an integral with respect to dx and dt.
Yeah.
Here you have an integral with respect to dp1 and dx1, right? So there must be a minus sign here. Is it not?
No, I don't. I mean, this is a 2D delta function. I could also take this to be all the sign it would also be,
Yes.
but I'm saying this is a 2D delta function. I don't think it's in any way inconsistent with these definitions, but we can talk about that afterward. I can try to sort that out. Right. I guess the last thing I wanted to say, and maybe that leads us, is to write the 2D delta function in terms of alpha, the complex amplitude. So let me now write a 2D delta function that's a function of alpha minus alpha prime. What does this mean? What this means is a delta function of the real part of alpha minus the real part of alpha prime times a delta function, the imaginary part of alpha minus the imaginary part of alpha prime. That's what a 2D delta function on the complex plane is defined to be. Something that the real parts are a delta function and the imaginary parts, okay? And this is x over root 2, this is x prime over root 2, and this is p over root 2, and p prime over root 2. And if I want, I could take the root 2's outside the delta function, but upside down, and I do that twice, and I get twice the 2D delta function. So that's another factor of 2 I must track down. God forbid. All right.
It just gets worse.
Yeah, unfortunately, it'll even get worse. Okay, I'm sorry. I did not invent this, although I wish I did. All right, so with that said, going back to Shravan's question, we can look back at the 2D delta function and write this as d beta over 2 pi squared. One of the 2's goes away, but the other one stays. And then I have e to the beta alpha minus alpha prime star minus beta star alpha minus alpha prime. which is equal to, from this expression, 1/2 delta, the 2D delta function like that, because that's what we just had. If I divide both sides by 2, I get this thing is that. You with me? Magic. Okay? And so we have this expression that we will use all the time whenever we use this stuff, that this is true. The Fourier transform of this thing is that. Okay. I'm sorry for those of you, but this is how it goes. All right, so with that, how in the world are we going to define a representation of states and operators? Of course, states are operators, but whatever. In phase space. Well, I have a suggestion. I'm going to define what I'm going to call the symmetric phase space delta function. Remember, let's go back to the board on the right here. We were saying that when we had the position or momentum representation, I could think about expanding the operators in a PLDM that were delta functions that replaced the operator P by P. And we had similarly for X. So let's define this operator. Which replaces X by P and P by, or X hat by X and P hat by the value P symmetrically. I mean, we can't write this. This is not equal. It does not equal this. Because who says X goes on the left and P goes on the right? That's not even a Hermitian operator, because if you take the dagger of it, it's not the same thing. I want to think about something that is symmetrical, okay? How am I going to do that? I mean, it's also not equal to this. It's somehow a symmetrized version. I want to think about something that's a symmetrized version of this, so I don't play favorites, you know? If you ever have kids, you can't love X or P better. You have to love them equally, all right? I don't have an X or a P, so. So how are we going to do that? The way we do it is we take inspiration from what's written over here, which is that the delta function that replaces the operator X by the value X was the Fourier transform of a plane wavy-like thing, which was the displacement operator. And vice versa. The thing that was the delta function that replaced P hat by P was the Fourier transform of a plane wavy thing, which was the displacement in position. But now we got to displace in both position and momentum at the same time. But we know how to do that. There's our friend, the phase space displacement operator that displaces in P and X at the same time. So we look at the phase space displacement operator, D, which displaces in X and P at the same time. It's got the momentum displacement. This is why the sign convention is like this, is because of the displacement. It's all about this. Okay, that's why those signs look like this. That's why I can remember it. This thing displaces in position by that amount, and it displaces in momentum by that amount, and it does so symmetrically. If I were to write this as a power series, it's that, which has all, it doesn't, if you, let's write this out. Let's write out the first, I got 1, I got plus minus I x p plus I p x hat, and then I'm going to get minus a half, I'm going to get x squared p plus p squared, or x squared p squared plus p squared x squared, and then I'm going to get minus xp times x hat p hat plus p hat x hat plus dot 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 when I square that out. And so I'm going to have, this thing is symmetric in x and p. The exponent doesn't care the order of x and p because they're in linear order. So this object is symmetric in x and p. And so now I'm going to define the 2D, this delta function, dx1 dp1 over 2 pi squared, e to the I p1 x hat minus x minus I x1 p hat minus p. That's equal to, what's written up here, the delta function x hat minus x, p hat minus p. It's the Fourier transform of the displacement operator. It's the 2D Fourier transform of the displacement operator. This thing is equal to d of x1 p1 e to the I, oh Lord almighty, minus xp1 plus I p x1. Let's breathe for a second. Well, I define here is the phase space generalization of what we had in wave mechanics in a way that you may not have seen before, which is that the projectors onto the position and momentum eigenstates are Fourier transforms of displacement operators. It's all intimately related to physics, right? That momentum displaces in position, and position displaces in momentum, and that duality is here. And we've defined now just an operator that is the phase space generalization, which is that I'm going to define this symmetric 2D delta function to be the Fourier transform of the symmetric displacement in position and momentum at the same time. Excellent. Now, again, horrible factors of 2 and pi. We're going to turn this into a complexified version of this. If I define alpha as x plus ip over root 2, and the annihilation operator as x plus hat plus ip hat over root 2, then the displacement in x and p is equal to our friend that we know by heart. That's what we sometimes call D of alpha. I also call it D of alpha. So this is the displacement operator written in terms of the complex amplitude and the annihilation operator. And with that, what we have is that pi times a 2D delta function this is the operator version of this. It says that this is my, I should really think about this as a function of both of these guys. But this is a symmetric in A and A dagger 2D delta function. Yes?
So, is this delta function a projector to the current state?
Oh, it's a good question. It's a
They
very
are not
good question.
orthogonal, so.
The answer is no.
Yeah.
The answer is no. The symmetric delta function is not. But as a harbinger of things to come for those who know, but you will see this next lecture, the anti-normally ordered one is, but the symmetric one is not. Come back to that. It's a good guess, but it ain't true. Okay, so with that, there are some things that are now generalizations of the plane waves and the delta functions on function space versus the delta functions and plane wavy-like displacement operators on operator space. We need to remind ourselves of the whole notion of an operator basis as opposed to a basis of functions or a basis on Hilbert space, sometimes known as superoperators. Okay. I told you. I told you to buckle in. If you were like one of those people on the airline who said, I don't care what the steward or flight attendant, I'm not buckling in, and then, you know, the turbulence comes and you hit your head, I'm sorry. I warned you this was coming. Yeah. It'll come back. Okay? So, operator basis. Remember, it's sort of like matrices. The set of matrices form a vector space. Remember, we had, for example, 2x2 matrices. We said that the identity sigma x, sigma y, and sigma z form a operator basis. As to say, any 2x2 matrix or any operator that acted on a qubit could be expanded in those things. In fact, they're orthogonal. And if I, put a 1/√2 on them, these guys are all orthonormal in the sense that we have an inner product, right? So I can think about the inner product between two operators or matrices through the Hilbert-Schmidt inner product. And so I can think about a vector in the matrix space. So, A here then goes over to some ket-like thing. Oh, God. It's a notation. It means that it's a vector in the vector space, and it can be expanded, for example, in some A alpha, in some basis E alpha, where say E0 or E sub alpha is 1 over root 2 sigma sub alpha. And these coefficients are the inner products, which is the trace of that. In this case, they're Hermitian, but who cares? Okay. Now, I can think about a complete set of operators as an operator basis, but it doesn't necessarily have to be orthonormal. It's something that, when I sum over all these guys, I get the super identity, dun, 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 which is to say, I can then do this, what I just did over here, say I take this operator, which is a ket, which is now, I sum over these guys, and I get an expansion, just like the one I wrote down. So, with that, in the same way that plane waves or momentum eigenvectors form a complete basis on the function space or in the operator space, the displacement operators form an operator basis. In particular, if I look at them in a complexified version, if I integrate over all beta with the pi in there, that's a hard thing to prove. I don't think I'll give it to you for homework because it's too hard. But whatever stopped me doing that in the past. It was proven in a nice paper by none other than one of our own professors, Professor Kevin Cahill, in a famous, yes, as some of us know, Kevin Cahill was Roy Valber's student. Roy Valber was also the advisor of Sudhakar Prasad, who was when Victor was Sudhakar's student many years ago. So Valber's your grand advisor. And Cahill did his PhD on this subject, believe it or not. Okay, what that means is that, and I can define similarly the delta functions, which I will call T, because that's what Cahill called them, and we all do now, which is, so T of alpha is the 2D delta function. Symmetric delta function, which is the Fourier transform of the plane waves, or the displacement operators. In the same way that momentum and position eigenstates form a basis of functions, the displacement operators, which are plane wavy-like things, and the delta functions, which form an operator basis. And I'll conclude with the following statement then. What this says is that if I have, for example, the density matrix, rho, I can think about it in the superoperator business. Write it like that. Okay? Which means that rho is equal to this times this function I'm going to call W. W of alpha is the trace of T alpha with rho, with the units of 1 over pi. Or, written equivalently, this is equal to the trace of delta x hat minus x, p hat minus p with rho. And this is what's known as the Wigner function. And I'm going to stop there, but I'm just going to, oh, maybe it's still somewhere? No, it's not. Maybe it's up over here. Yeah. No, it's not. Okay. I want to just remind you, we had the probability distribution in X was the trace of the delta function with rho, and the probability distribution in P was this, right? This was the projector on X. This is just the general, I mean, all this formalism is just somehow getting to this point, that I'm going to define a joint probability distribution on X and P as just a symmetric version of this. The Wigner function, this is what's known as the Wigner-Weil representation. We'll come back to that. But the Wigner function is what's known as a quasi-probability distribution. It can't be a true joint probability distribution on X and P. Otherwise, I can do that. But it's quasi in the sense that it gives me a representation, but this can be negative. This guy is a Hermitian operator, but it's not an operator that's positive. It can have negative, which means we have some notion of negative probability. And that is a story that we will continue next time. I know this is a lot, the fire hose, dry yourselves off, but we'll see this in the notes and on TV, and you can think about it some more. But the thing I really wanted at the end of the day is you to just come away from is this final formula and the relationship, the dual relationship between the delta function and the displacement operator. Okay? All right, very good.